This is video 30 in the lecture on the design of reinforced concrete beams. This lecture deals with shear resistance of a cross-section with shear reinforcement. We will look now at the relation between shear reinforcement and shear force. We use the analogy of a truss system. The blue elements are the compression elements, the green are the elements in tension. The support is here and this is further on. The distance between two tension rods is Z cotangent theta with Z the lever arm and theta the angle of the compression strut. The total reinforcement available in one tension rod, vertical tension rod, is ASV, and this is equals to the number of stirrups in this zone, is the number of stirrups in this zone, which is Z cotangent theta divided by S, and S is the distance between the stirrups, and ASW is the cross section of one stirrup. For two legs, it's 2 times the cross section. So if you now want to calculate what is the stress in the tension rod, the vertical tension rod, well, the stress then is equal to the shear force divided by the total cross section of reinforcement that is available. If you substitute, then we have this relationship. It means that at the limits, when V, the shear force equals the ultimate shear force, Vu, then the stress in the stirrups is then yielding, is then equals to FAWD. Then we have this formula, which is giving you the relationship between the shear force, Vu, and the shear reinforcement, which is ASW divided by S. And theta is the angle of the compression strut. Now let's consider this equation that we just now found, and on the x-axis we put the shear force, on the y-axis the stress in the stirrups, Now this equation means that if you keep your stirrups or your shear reinforcement constant, Z is also constant, cotangent theta is a constant, then you know that there is a linear relationship between V and sigma SW. This relationship ends when sigma SW equals FAWD. So this equation means the green line here. That's what you expect. But when you do tests, you measure the red one. This inclination is the same as this inclination, but in the beginning you can take more shear force for the same stress in the stirrups. So this portion. The difference between those two lines is the shear force that can be taken up by the concrete itself without the shear reinforcement. So this is an important thing to notice, because we will see that the ultimate resistance of the against shear is only the contribution of the stirrups is taken into account, and not the contribution of the concrete itself. This is the truss system again. It's a little bit more general. The angle of, or the inclination of the compression strut is theta. The inclination of the stirrups or the shear reinforcement is alpha. And according to Eurocode 2, the cotangens alpha must be between 1 and 2.5. The National Annex of Belgium changed it a little bit, and the cotangens theta must be between 1 and 2, but you can increase it by a term depending on the normal compression force available at the section. But it can never be bigger than 3. Let's now consider an isolated system where V is the shear force and T is the tension in the stirrup. Then alpha is the inclination of the reinforcement, theta is the inclination of the compression strut. We know now that V is equal to T sinus alpha, and T, the tension in the stirrup, is equal to the number of stirrups in the zone considered times the cross-section of the stirrup times the yield stress of the stirrup. And the number of stirrups are, of course, Z cotangens theta plus Z cotangens alpha, divided by the distance between the clear distance between the stirrups. And with this force, you can take up a shear force which we call VRDS. So the design value of the resistance to shear given by the stirrups only equals, if we substitute the T in this formula and the N in this formula, we have what is written here. Just remember, cotangens alpha is 1 for if alpha is 45 degrees, but in most cases alpha will be 90 degrees, so cotangens alpha is 0 and sinus alpha is 1. A more general approach can then be found in this drawing, where Z is then the lever arm between the compression zone and the tension zone, theta the inclination of the compression strut, and alpha the angle of the stirrup. And then we have seen that VRDS is N times ASW FAWD times sinus alpha. So in fact this is just the force in the stirrup section, and the number N is then equal to this. The design value of the maximum shear load resisted by shear reinforcement, and this at a given shear reinforcement, is then equal to this formula that we have just now seen. But in most cases we are looking for the needed shear reinforcement, so we just turn this formula around, and you will see that ASW divided by S, the needed shear reinforcement, is equal to the shear force divided by the yield stress of the stirrup divided by the lever arm, and Z equals 0.9 D, with D the effective depth. You can have a quick guess of the shear reinforcement when you need the diameter, for instance, and you can do it as follows. We know that VRDS is given by this formula. For vertical stirrups, which is most of the time the case, it means that that sinus alpha is 1 and cotangens alpha is 0. Then we have this simplified formula. And FAWD for B500 is 435 megapascal, Z is 0.9 D, and cotangens theta, we take 2, the maximum value for cotangens theta, which gives you the minimum amount of reinforcement. And then you can easily see that the needed reinforcement, ASV over S, equals the shear force divided by 0.8 times D, the lever arm. Just take care, D is here in millimeters and VRDS is in kilonewton. So that gives you a very quick estimate of how many stirrups you need. You can compare that where you calculate the needed reinforcement due to bending moment. You can simplify this and you can estimate the amount of needed reinforcement by just dividing the bending moment by 0.9 D divided by the yield stress of the reinforcement. So those two formulas are quite similar. The maximum shear load that can be resisted by the concrete compression strut, you know, it is a truss system, and we have now checked one leg, which is the tension leg. Now we will check the compression part of it. The maximum available shear force is then the maximum concrete stress allowed multiplied by the area of the concrete strut and taking into account of the direction of the strut. So this means that the maximum concrete stress is the FCD times the width times nu, which is a reduction factor. And the dimension of the strut, the width of the strut, the strut, is equal to z cotangos theta plus cotangos alpha times the sinus of alpha. If you make a little drawing, then you can easily see the relation between it. So we got VRD max. We know what the strut is, and if you fill it in, you have this. If you have this equation, sinus squared of theta, you can transform it in a very simplistic way into 1 over cotangos quadrat theta of cotangos squared theta plus 1. And then we have this formula. We transform everything to cotangos theta because we are working in all formulas with cotangos theta, not necessarily with theta, but with cotangos theta. We know this should be between 1 and 2 according to the national annex. So it's easier instead of working with sinus theta. So this is easier to use. Alpha is most of the time is 90 degrees, vertical still-ups. And then you have this classic formula. But if you do that, then you need first to have a guess of cotangos theta. Let's say you take it 2, then you can calculate VRD max. But what is sometimes handy to do is that you know what the maximum shear force is at the support of the beam, and you do it in the other way around. You calculate the theta needed to take this maximum shear force. So sometimes this is a quicker way of dealing with the matter. That's why this formula is written in sinus 2 theta, because this is more difficult to calculate cotangos theta. The maximum shear load that can be resisted by the concrete compression strut was VRD max, like we have seen just now. The nu is 0.6 times 1 min FCK divided by 250. FCD is alpha cc FCK divided by gamma m, but alpha cc is in this case here 1, because it's not bending and or normal force. It's 1 here for shear force, and punching alpha cc is according to the Belgium annex 1. The sinus theta equals d strut divided by z cotangos theta plus cotangos alpha, and it gives us or the d strut is equal to sinus theta times z and so on. If you take all that into account, you have the formula VRD max as it is given here below. Remember that we are working with a truss system. We have already seen the tension in the stirrups. We have seen the compression in the compression strut, and there is one element left, which is the tension in the longitudinal direction. Because of that thrust model, we know that there will be a force or a tension force in the longitudinal reinforcement. The shear force is V, and C is the compression force in the concrete, and S is the tension force in the longitudinal reinforcement due to the bending moment. Then we know that T is the tension in the stirrup, and the D is the compression in the compression strut. If we take now the horizontal direction of D and T, then we have these equations, and we take a equilibrium around a rotation equilibrium around S and a rotation equilibrium around C. Then we have those two formulas. It is the bending moment is equals to NC times S, and then we have dx and tx times z over 2. You see that dx and tx have a different sign because they work in a different direction. And this is exactly the same, but an equilibrium around point C. Now, if you can see by those equations that there is an additional tensile force in the main reinforcement equal to this portion. Now, it is the shear force divided by 2 times cotangos theta min cotangos alpha. At this additional force in the reinforcement, but due to bending, it is only bending moment divided by z. But there is now one portion that is added to it, which is delta FTD. But there is a maximum to it, and the maximum should comply with this equation. So the maximum is between MED max and MED at the location where you are doing your check. So you can see it also in another way. You can, for instance, it's a mathematical trick. You can shift the bending moment diagram over a distance z over 2 cotangos theta min cotangos alpha, and then you calculate your needed reinforcement for that bending moment. Then you don't have to take into account the delta FT. You can notice that if the stirrups are inclined at 45 degrees and the strut angle is 45 degrees, then you need no shifting. Delta FT is then 0. The shifting of the bending moment line can be easily explained. Suppose this is the original bending moment. In the middle here, you cut it and you shift it over the desired distance, and you arrive at this bending moment line. And because this line is shifted, it looks like it mimics the effect that you increased the tension in the tension reinforcement. You see that the delta FT is 0 when the bending moment is maximum, and is maximum when the bending moment is 0. You can now calculate the needed stirrup reinforcement of a cross section. See you at next lecture.